Start by doing a couple of housekeeping. One, I first of all need to start by apologizing because, as I have mentioned to you in week one, I don't read the unit outline, and you should understand that the unit is a national unit. So the unit outline that you see applies to both the school in Queensland, Victoria, and Disney. So before this semester we had some meetings in which we agreed, okay, this is to go and blah blah blah, and we were arguing. The lecturer in Victoria wanted to do the client report, and I was waiting for the research project. So we agreed that the two items were to be listed for you to choose one of them. But I didn't realize that she took the research project out of it. Which should be. So and that's why I presume a number of you guys were asking exactly what the assessment is, the research project. And I had the wrong idea that it was included in the unit outline, but someone mentioned that to me today and looked at it and it is not, which is a bit disappointing. But that's life. So by early next week, you will have a clear description of what it is and what you guys are going to do with your data and how you are going to present it. I do, however, believe that I can explain this to you, but it's best to have it in written so you have something to refer back to at any time. So apologies for that, and that will be rectified by early next week, if not before. That is point number one. Point number two, and linked to it, is that some students were asking whether you needed to submit proposal by this week, and the answer is no, you don't have to submit anything. All you need to submit to us is the report when it is completed. And of course you have the midterm exam, which is in week 5 at lecture time, and the final exam. Talking about the midterm exam, we'll keep working on that, but essentially what you guys are going to have is a very easy exam that will comprise of 10 multiple choice questions, 10 MCQ, to be honest, I don't remember, but there will be a number of short answer questions. I don't remember how many there are. I think there are 4 or 5. And you will have 2 long answer questions. I will upload by the end of next week some more study questions that will gear you up for the midterm exam. So you should expect by early next week to have a clear description of the research project, and you should expect by the end of last week some study questions that will have MCQs, short answer and long answer, so you are more or less prepared for it. What will be covered in the midterm exam is the content covered between weeks 1 and 4 inclusive. So whatever we do next week will be covered in the midterm exam. And just to make sure that you guys are not surprised, the final exam will cover the 12 weeks plus anything that might be done in tutorials. So the final exam is a final exam. It comprises all crafts together. Okay. And again, in the report, in relationship to the report project or research project, sorry, students still ask me whether it's a group or an individual assignment. It is individual. Each of you have chosen what topic you're going to report on, and that is what you report individually. So it is not a group assessment as it is indicated in the unit outline for the client proposal, which is something you guys are. Okay, again, I will upload some documents on this so you guys have more clarity on that. And just so I don't answer the same question many times too, once you have digitized your data, whether as in last week, this or next week, all I need from your video data is the data to be filtered. If you have eagerness, you can go up to define segments. That would be head, trunk or torso, thigh or upper leg, leg or shin as you call it, or shan, and foot. So those 5 segments, if you can do that, do it. If you cannot, it's not a big deal, but it will certainly save us time later on for you to have done that by week 5. And if you are game enough, you can also do segment angles. Yes. You can do segment angles. And that will be for the trunk, the thigh, leg, and foot. If you really want to keep doing this, you could also do the joint angle for the hip, knee, and ankle. As we have done, this we have done in week 1, so you should be able to do it quite comfortably. Once you complete doing that, you can leave your data to rest. Until we have to choose in week 5. A note on this is that the week of the midterm exam, the first 45 minutes obviously is for the exam, and then we'll have a lecture after that. So don't assume that because you've done the exam you can walk away. We only have 12 weeks to do what we have to do, so we have to make the most of it. Okay, do we have, or do you guys have any questions that change this? Yes.
Did you say we're not doing a client report anymore?
No, you're not. You
So
have.
that's just
You never worked with it.
Ignore that.
No.
Beautiful.
So that's what I'm saying. I will describe better the research project in a document so you can actually refer back to it. But you are not doing the client report. Okay. Yes.
Just in regards to the students who have classes on Friday next week, that's Good Friday. Do they just dissolve into another class?
Yes.
Okay.
If they can do it, yes. That would be ideal. Okay. What you were doing with your hands. I just saw you doing that. Okay. Okay, let's just quickly recap what we have been doing so far to link it with what we are doing today. Suzanne, thank you very much. Are you done? Yes? Finish saying what you have to say to each other? Say goodbye until the next half an hour. Okay, essentially we've been talking about the strength of materials in a roundabout way, but essentially that is what you have been doing with the notion of applying this concept to human biological tissues in order to make the understanding of bone tissue, ligament, tendon, muscle easier, because after these lectures I would like to think that you understand the basics of the strength of materials and how that actually relates quite well to human tissue. When we get to deal with ligament, bone, and tendon in some joints next week, I will not do it from the point of view that you have done in anatomy. It will be pointless for me to repeat content that I should assume you guys know. So I will address those, but from a purely mechanical point of view. So that is why anatomy has been put as a prerequisite to this unit, to make sure that you guys understand that part well, so we don't have to be repeating it. So again, I'm just making the point that whatever we do next week will have very little to do with anatomy. There will obviously be crossovers, but what you guys are going to see from me is the biomechanical aspects of it. So don't expect that I will refresh your memory on that, because I won't. Okay? So essentially we were looking at the strength of materials with the view of applying these concepts to human tissue. And there are some things that we have covered, I believe, reasonably well, and that is stiffness. So that's, I believe you guys understand well. We have covered the stress and the strain relationship, and you guys understand as the stress increases, the strain too increases in a linear fashion. And that has been explained by Hooke's law. You guys understand that there are many types of stress depending on the direction it is applied to an object. And out of these two, we got to be able to calculate the Jarvis modulus, which essentially is the same as stiffness. It's just that more accurate. But from a physical point of view, they describe the same phenomenon, which essentially is how easy or difficult it is to deform or to strain an object. Obviously, we have covered the formulas for each of them, and I will understand that you understand that reasonably well. So we will transfer these concepts along with the ones that I will present to you today to biological tissues next week. One thing that I did not mention was the idea of density. So we'll start off by looking at, I have made my notes as to what it is I need to cover today. I will start off by covering density. Actually, there are many points, but hopefully I'll be able to make it easy to digest. On this, I would stress the fact that attending or listening to this chat is not enough, obviously. You need to complement by reading the notes that are up on here. And that is certainly not enough either. You need to complement that with further readings from your textbook or resources that you can find in the library or on the web. So don't be content by, don't be happy with the fact that I'm coming to the lecture so I should know it. It is not true. Make sure that you couple at least with your readings, at least. Then your readings will become easier to digest if you can, obviously, than if you don't. But you need to complement it. So sometimes I might say something that is not well perceived by you, so you have the chance to reread that and make sense out of it at your pace. Okay, so I have got a few points that I want to cover, so I hope I'm not being too ambitious, but let's see how we go. Okay, we'll start by talking about density. Density essentially is a physical property of any object that describes the mass to volume ratio of that object. The name of density is specific weight. That's a proper name to it, but we commonly use the term density as such. I don't want to give you more symbols for it because that might confuse you, so I'm just going to use capital D, which is used in some textbooks, but there is a specific symbol for it that I will loaded with that. We have said that density is a range of mass to volume. How much volume does a mass of an object occupies? And that is calculated as mass divided by volume. So for a given mass, the larger the volume, the less dense the object is. Have you ever tried to float on water on your back, doing nothing? What happens when you do that? If you are trying to say that's water, that's you, that's your chest, your foot, your arms are there, you try to float there on water. Can you manage to float flat horizontally without doing anything?
The legs.
The legs sink. Yep. Why would that be?
They're more dense.
It's higher density. There is less volume but more mass. You have more muscle mass, you have more bones. So the legs then sink. Whereas the upper body does not, because we have the lungs, we have these cavities that have volume but do not have as much mass as the leg. So they tend to stay afloat. If you have a gymnast doing this, the gymnast will sink altogether because they are highly dense. If you have a sumo wrestler, they probably will float because they have a large percentage of fat. And as you know, fat is not as dense as muscle. So that is a simple way that I think I could make you relate to the idea of density. So essentially, density measures how much volume a given mass takes. If the volume that the mass takes is small, the object is more dense. If the volume that the same mass takes, then the object is less dense. It tends to stay above, say, water, if water has a density of 1. If you are into the habit of eating soup, yes, you will see how some elements of your soup float. It's simply because those have less density than the soup itself. You can see how the fat content of the soup might be on the surface because fat is less dense than the water, if that makes sense. Essentially, that is what density is. And why are we talking about density? Because density is an essential property of an object. So when you have an object, whatever this object is, you want to know, on the one hand, the physical dimensions of the object, that is the cross-sectional area of that object, which is something we didn't talk about. You want to know the resting length of that object, that's the physical dimensions of it. You also want to know, as we talked about before, what the stiffness of this object is, how hard or compliant this object might be. And the other property that is important for us to know is the density of them. And that is what we are talking about. Laurel, do you want to change places? Okay, change them. Come here. No, come here. Huh? No, it's not alright.
It is alright.
Okay. So we have these properties now. Although density and stiffness, they do measure molecularly different aspects of a material. They are not the same thing. Experimental studies have demonstrated that as the density increases, so does stiffness. So there is a direct relationship between them. What that means in simple terms is the more stiff an object is, the heavier it tends to be. That is what it means in simple terms. If you are to design an object that is going to sustain stress continuously, ideally you would like that object to be stiff. So then we could then choose for a denser object. The challenge with objects that are dense is that they are heavy. If you have something heavy, then it stops being functional. So if your pens were heavy, then they wouldn't be functional. You wouldn't be able to use them as regularly as you can. So that is a challenge that nature imposes on us. That clever engineers have designed materials that are both stiff but light, due to the creation of some composites. And that is what it is used when processes presumably have to be done. But we will talk about that further down the track. So at this point in time, I'm happy with the notion that if you plot density versus stiffness, they have a linear relationship, or more or less linear relationship, indicating that as stiffness increases, so does density. With this, we can play a bit with the mass and have things that I hope will make sense to you. Say you have an object such as this. That is subject to a stress. That stress, as you know, is calculated as what? Force divided by the cross-sectional area. So that being the cross-sectional area of that. Yep, that is good. So what can we do with this? Say we know the density of this object. Density will be equal to its mass divided by its volume. Of that object that has a CSA cross-sectional area and an L0 resting length. We can rewrite this and say that the volume equals mass divided by density. I'm just swapping these two in the equation. Is that okay with you guys? Yeah? What is volume equals to? The volume of that cylinder is equal to cross-sectional area times resting length, isn't it? Because it's a cylinder, it's cross-sectional area times length, which is the volume of that cylinder. We'll
wouldn't the Z could be M over D, wouldn't it be B and times D because you're reversing it?
Now this is coming here times D, correct?
Yeah.
And D is coming to the other side divided. Again, you are saying, is that correct?
Yeah.
Okay, if I want to leave V by itself, will this then be?
Oh, okay.
Yeah?
Sweet.
Okay, so we're going to replace this equation here. The cross-sectional area times resting length equals mass times density. Yes? What is cross-sectional area equals to?
Right.
Cross-sectional area will be equal to force divided by stress. Yeah? So if we replace cross-sectional area by this, we are creating a very unfriendly equation that relates stress, density, force, resting length, and mass. Ah, yes, sorry. No? You want to give up? Okay. Again, the purpose of this is to show you how the basic mechanical properties of an object are interrelated, they are not independent. Obviously, I don't expect anyone to remember this. I do expect you to understand that they are related. That's it. Okay? When you guys go through the calculation questions on your notes, you will see something similar to this being applied that will finish making sense out of it. Okay, let's just move on to something else I want to cover. Now we'll just refer back to what we have called last week atomic model. Assume we have two atoms of an object. These two atoms are linked, at least theoretically, by a spring. That is a modeling artifact that we do. And we call this spring atomic bond. So it's what keeps these two atoms together. Essentially, it is what keeps the object integrity together. Last week we said that if we are to change the shape of an object, essentially what we do is to change the length of this atomic bond, for which we need to invest energy in changing that bond. So this bond is a force, the interatomic forces that keep them where they are. If we want that to be altered, those forces have to be altered somehow. And we are going to describe here three different situations that I think are important for us to understand. When external forces are applied to these atoms, we identify three ways in which this will deal with them. One way is this. So you have the two atoms have the atomic bond. One way is actually let the forces run through the atomic bond and keep passing on, such that this atomic distance doesn't change, such that this atomic bond is not altered. These guys are just simply allowing the external force to go through them without absorbing any of them, without being affected by them. This simple description, of course, is simplified, is what materials such as crystals and ceramic do. They let the external force run through them without altering their shapes. And that is not, it's not a casual, it's not by chance the fact that when you hit crystal or ceramic, the noise is high. Because that energy that is being spent is not altering the atomic structure, but is being converted into noise. So ceramic and crystal actually are the loudest. Any structure that is loud on impact will tend to have this, because the energy that is put into them is converted into sound waves. And these guys here are important for us as humans, and we'll see that later on. The other option is for these atomic bonds to accept the external forces that are acting on them and allow that to alter the atomic bond or to alter the atomic distance in between. So these guys will get closer or further apart, but that is within a range. And as you guys know, that will be done within the elastic range, which is something that you already know. Such that when these forces cease or stop being applied, that will be returned, and the object will return to its original shape, which is what we know as elastic deformation, which is something we have seen last week. And the other alternative for this is to allow these forces to alter the atomic bond past what we know as the yield point, time after which the deformation will be permanent, which is what we know as plastic deformation. So the energy will be uptaken by this, and this will be permanently changed. That is what we know as plastic deformation. I'm not sure whether we have said this before. In point number 2, the elastic range, I conveniently says within a limit, but I didn't say what limit this was. This is true up to 10% of strain. So most objects will deform within 10% of the strain in and within the elastic region. Seldom an object will stretch beyond that and remain elastic. Of course, there are some tissues who do that, but most objects only function within the 10% range of strain, 10% or less. What this means is this. and strain. So 10% would be 0.1. Yep. Just have 0.1 here. What it means is that the stress strain curve is linear up to 10% or up to 0.1. Out of asking you a bit, what kind of stress would this be representing?
Elastic.
It is elastic, yeah. Would this be, what else would you say about this?
Tension.
Tensile, yes, because the strain is positive. That means that the object is getting larger. Yeah. Does that convince you all? Yeah. How would the compressive strain look like?
Like this.
Sorry? That opposite?
A bit down.
Going down.
Yes. So that would be compressive. Yeah. So that is tensile and that is compressive.
We were saying 10%,
Yep.
so it's linear up to 10%.
Yes. Time after which it will stop being linear.
So after the elastic growing.
What happens is this. When you measure strain, what is the formula for strain? Resting length and not actual length minus resting length divided by resting length. Correct? Yep. That's your formula times 100 if you want to. Okay. I'm just trying to make you think without, unfortunately, I didn't bring my elastic bands to my shoe. Say we have that string, that is its resting length. Yep. And you apply a force on this, and that will stretch to here. That length we call L. And the strain will be calculated by using this equation. Yep. Now, say we keep stretching it. This is the same strain. Say that is resting length. From this point, we keep stretching it to here. That will be the new L. Am I making sense with it? When we calculate the strain, which is the resting length we use? Do we use this or do we use this?
Original.
Say you have your string, resting length. Step one, we stretch it from here to here. So to calculate the strain, we say is this length minus this one divided by this one, correct? The step one here. Now, step two, from here we stretch it here. Do we use the same resting length, or do we use that as a resting length?
Same resting line.
What happens is that when you use the same resting length, it will not work, because at one point when this fails, strain will be approaching infinity. Am I making sense? Because the difference between this, the original, and then you have 100 meters is significant. And you divide it by this small number, you have a strain that is actually quite high. What has been demonstrated empirically is that it is best to use the strain just before the actual stress. Does that make sense? No. I'm just trying to think of, if you have resting length, stretch it by a bit, that's your L. If you keep stretching it, it will be here. If you keep stretching it, it will be here. If you keep stretching it, it will be here, and so forth. What has been demonstrated experimentally is that the strain is best calculated when you use this value as your new resting length. And for this, you would use this value as a resting length. That as a resting length, and for that as a resting length. Just the one before. Does that make sense?
So is that just after the elastic range, just after the elastic range and the instantaneous thing?
And you keep stretching this and you use that as a resting length. So just the one before.
Isn't that because every new stretch after that, the strain's a little bit less every single time? It's not.
That's exactly
Yeah.
what I'm trying to get. As you keep stretching this, and as the resting length keeps increasing, the strain starts to decrease. Yeah? Such that the curve or the true strain deviates from this and behaves in that fashion.
It wasn't past that 10%.
Yes. So it stopped being linear. The other point that is important to keep in mind is this. Say you have that object. You strain that by applying a stress on it. So that object will increase, will be longer. Correct? By this much. The question is this. Is this cross-sectional area the same as this? If the stress is tensile.
It's gone skinnier.
It elongates.
Narrow.
It will have to narrow. Because if it doesn't narrow, that means that we are creating more mass out of nothing, which is impossible. So if you make it longer, then it will have to be narrow for it to be the same quantity of matter. So as you keep stretching this, the cross-sectional area starts to get narrow and narrow. The impact of that is that the stress starts to increase. Why will stress increase? Because the stress is calculated as force divided by the cross-sectional area. So if the cross-sectional area starts to decrease, then the stress will naturally increase as the object becomes narrower. Does that make sense? Or not? So those two corrections to the stress and strain concept have to be implemented when we start dealing with more real objects. So in theory, we can say, well, they are linear, but when we look at the dimensions of this, then things need to adjust too. Okay, this has been quantified and has a particular name. That's the Poisson's ratio. You don't really need to remember the formula, but it helps to fully understand it. Essentially, quantifies the relationship between the strain about the cross-sectional area in relationship to the strain along the longitudinal axis of the object. That x, y comes from the fact that we have here the x-axis, the y-axis, and here we have the z-axis. So that is where this comes from. It actually quantifies the strains horizontally or across the cross-sectional area by the strain on the longitudinal axis. Yes? What? I'll be in Greek. Yeah, don't worry too much about the variable. I don't think you will use it more than understand it. You will think you understand it. Okay, take a little break. Take a little break, please.
Oh, but I'm the same. Oh, yeah. Every time like, you know, I was describing to one of my other mates what I figured out from the lectures every week. Like, I mean, you've got 1 week to go through this concept, and it's possible if you're trying to understand and remember a concept in 1 week, you're going to drive yourself insane. I think the goal with uni is to understand. Yeah, exactly. Because it takes time. The bit that takes the longest time is to understand. Yeah, because you have to do all this research. But once you understand it, you read the sentence in 5 minutes. You understand what is going on.
That's what it is.
Yeah. Yeah.
This morning I watched the experience.
Yeah.
I know how
Yeah, but you don't remember it. Yeah. A little bit. Yeah. Yeah. I understand. Yeah, exactly. And the bit where you do when you refine it to actually remember it is a week out from the exam. That's when you remember the shit. Then, yeah. Yeah. Yeah, that's a good point you made. Because then they're trying to understand and remember in fucking in a week, and yeah, you're gonna just have to.
So what you just said now,
Oh, it's just like
Yeah. It elongates.
that is that stretch.
they know what I'm wrong.
I fucking don't remember the formulas. I don't remember it.
We got a formula sheet.
We have bad habits.
For this one though, I understand what you're trying to say. But if you've got this, say you've stretched that to that realistically
Yeah. Oh no, I cut that one. Yeah. Oh yeah, I got 2 recordings. The battery's got it's got 10 minutes left. And then I've got to do like that because it's going to take up all my. Actually, I was uploading the other one. I'll do it again tonight. I was uploading week 2, but it got to 67% and then it just stopped uploading. I need to do it again tonight. I'll do both of these ones.
If we didn't calculate these ones, you would have to use those two versions. You have to and if it's compressive, it'd be a negative. Each side of this, and then with this, that would be your new L, and your minus from that. That's what he's talking
I wonder, but I